what science is. And so there are two readily available answers that are given to this question. One is that it's a body of knowledge, and that's how we first learn about science as children, right? We just learn facts of, the sun is the center of the solar system. And eventually, much later, we are introduced to it as a method, right? It's a method for generating and evaluating knowledge, right? This is when we learn about how we know that sun is at the center of the solar system. There's a third way of thinking about science that isn't discussed as much, that doesn't get as much attention, and which is the thing that I'm glad to hear that most people agree to, which is that it's a way of thinking. And so scientific thinking, we can think of it as sort of an approach to understanding the world around us, and that need not be limited to scientists, right? There are certain core features. So this is Carl Sagan. Science is a way of thinking much more than it is a body of knowledge. So there are some core features, right? Our methods might change. We might change how we do things. We might, right? All our beliefs, all our knowledge is provisional. We change it in the light of new evidence. But there's certain core features of scientific thinking that I think sort of stay true to science. One is just the belief in objective reality, right? There's a world out there that's independent of us that we're trying to understand with science. And there's a drive to understand reality through empirical observation, right? Actually observing what's out there, not believing everything that we are told, right? Not believing everything you're told, and then thinking critically about the claims and arguments that are being presented, right? And these all are sort of features of scientific thinking that I think everybody can benefit from, not just scientists, or right, not just people who are evaluating and generating knowledge, but everybody, right? So for us, things like, okay, correlation is not causation, is almost like a platitude. But if you're somebody that's reading news, right? If you're a teenager or a parent of a teenager that reads news now on, social media is linked to higher depression, it's useful for you to know what kind of data lends itself to causal claims and which not, right? So these are useful tools that everybody can benefit from. So how can we make science more accessible for non-scientists? So one of the projects that I'm, again, very fortunate to be a part of is called Sense and Sensibility in Science. This is originally a course here at UC Berkeley that was started by three people. The first is Saul Perlmutter, who's a Nobel-winning physicist, professor of physics here at Berkeley, John Campbell, who's a professor of philosophy, and a social scientist, Robert McCune, who's a social psychologist and a professor of law at Stanford. And so the goal of this course was to equip students with scientific tools and ideas for evaluating and using information. And the idea that sort of weaved throughout the course is, how can we use scientific thinking to make better decisions and solve big, complex problems? It's now being taught at Harvard, where I think they wanted to call it Pride and Prejudice and P-values, although I don't think they were allowed to do that. And it's spread to other courses, to other universities, and we're not trying to adapt it for high school students, modules that high school students can be taught. And they just wrote a book, the three of them, called Third Millennial Thinking, to share the ideas from this course with a general audience. It's actually coming out at the end of this month. So if you're interested, if this sounds interesting, I would recommend it. So what are these ideas? The course is sort of split into these three parts, where we first talk to students about, what is the nature of science? When is it relevant? How do scientists make sense of the world using senses and instrumentations, and right, how do they get a sense of what reality is, what's out there? Then the second part is split into, what are the tools that we use, right? Tools for evaluating data. This includes things like, statistical and systematic uncertainty, probabilistic thinking, correlation and causation, and also like biases, right? How do our heuristics and biases, human biases, affect the way we do science and the way we evaluate results? And also when science goes wrong. So what are the markers of science that's pathological or pseudoscience, or just poorly done science? And finally, the last part is sort of tying it to the broader society. And as we were talking about earlier, of citizen science, right? How do we include the general public and other stakeholders in making better decisions? How do we use these scientific tools to make better decisions as a society? So it's a really well-rounded course that I think helps students, regardless of whether or not they will go into science. So why is it important to open everybody, right? To give these tools to everybody? One is, of course, right, I think knowledge is becoming increasingly complex. We just in the last year, right? I mean, AI has taken over. It's becoming so hard to figure out what's true and what's not. There's often conflicting information that's out there, right? What are the primary causes of global warming? Like, how safe are vaccines? Is AI going to kill us all, right? These are conflicting information available out there that people need to make sense of. There's a lot of pseudoscience, so it's also becoming harder to tell good science apart from pseudoscience, and also difficult to identify true experts from charlatans that are sort of all over and now more accessible to everybody. And more subtle, but I think more pernicious is the issue of, it's the classic issue of, there's lies, damn lies, and statistics, right? It is so easy to misuse data to suit any narrative that I think people need, some amount of fluency with understanding these features to be able to figure out what's actually true and what's not. And it's no wonder that trust in science is declining. This has certainly been in the case in the US for some time. Americans' trust in science continues to decline. And I was trying to figure out how things were in Finland, and I'm sorry if this is too small for you to see, but this is from 2019. So things definitely changed in the US after the pandemic. I'm not sure if this is the case in Finland. Generally, it seems like, people are mostly positive about the standards of science and technology and the quality of research. But more than like half of people are either don't know or are a little bit negative towards, impartiality or independence in research, or whether it can benefit everyday lives, and a little bit more negative in terms of trends in research activity in recent years. And whether it's focusing on important topics. And this is a little bit worrisome, but also related to what we're talking about, which is, right, are the general public being informed properly about science and its findings? But a little bit more positive than the US, I think. So, we, of course, want everybody to be able to participate, to have citizen science, to have, to be part of the scientific enterprise. Galileo said that in questions of science, the authority of 1,000 is not worth the humble reasoning of a single individual. But of course, right, one can only reason humbly if one has a critical thinking skills that are necessary for scientific criticism. Not everybody is equipped to criticize science properly. So in order for everybody to participate, I think we need to make sure that these tools are open for people to be able to use for this criticism. So this requires, sharing these tools so people can evaluate and use scientific knowledge and understand the scientific process. And one of the other projects that I'm very proud of to be a part of, where we talk about the process of science, is a podcast called Nelius and Verba, which I co-host with my dear friend, Dr. Daniel Watkins, who's over in the Netherlands, in your neck of the woods, relatively speaking. And the title of the podcast comes from the motto of the Royal Society in England, which is the oldest scientific society in the world. And it essentially means, take no one's word for it, right? Check for yourself. And trust but verify is another way of putting the same idea. And science is essentially organized skepticism, right? We're skeptical of any claims. And so these are the kind of things we discuss in the podcast, things like what is the role of skepticism in science, but also trust. What is the role of eminence, and like how much should we revere authority in science, right? There's on one hand, we have, standing on the shoulder of giants, but also, right, we should be skeptical, and science builds once we tear down older ideas. We also discuss things like confirmation bias. How do we build theories, and how do we build a cumulative science? So we talk about topics that we think are important in the way science is done in every day, but there's no forums to really discuss them. So we try to get these ideas and also talk about how can we improve the scientific process. And so I want to talk about the scientific process. Typically when we're introduced to the scientific method, it's described as a linear process, almost like a cookbook, right? You pull a question off a shelf, you throw in, you sprinkle in a hypothesis, you put this mixture into a pre-existing mold of research design, put the whole thing into an experimental oven, and then you observe, and which is to say collect data, until the conclusions are baked. You can garnish it with qualitative observations and then serve them up with grand claims. And we, of course, know that this is not how science is done. It's not linear. And as Lydia has mentioned, right, the results are never as clean and unambiguous as we have, as the storylines that we're often reading in papers. But about 12 to 13 years ago, especially in psychology, and some other disciplines like biomedical science and other behavioral sciences, we realized that things were a lot worse. So how we used to bake the cake and sometimes still bake the cake, and this is a bit redundant, but we keep putting the cake back in the oven at different temperatures until it comes out how we want. That's what we know as p-hacking. We throw away half-baked cakes. It's publication bias or conflict of interest, where we're trying to suppress unfavorable results, act like we wanted the half-baked cakes all along, which is, again, harking, hypothesizing after the results are known. Be stingy about ingredients, so that's lower underpowered studies and replications, which are less likely to find results. Add in fake ingredients, which we are now realizing that might be more common than we originally thought. And this is just, straight up data fabrication or falsification. So this, of course, led to the famous replication crisis, which really was, it's, an important moment that happened, and it started in 2011. So I will give you a little bit, like a brief history of how things went, at least in psychology. So in 2011, and Lydia has alluded to some of these, there was a famous paper that was published by Daryl Bem in 2011 in just a flagship journal for social psychology, the Journal of Personality and Social, Feeling the Future, where essentially he presented 9 experiments that supported the evidence, that supported the claim that people can be influenced by a future event. So essentially saying that ESP is real. And people realized that the methods that were used were not that different from the methods they were using, right? So if you're able to show something to be true that clearly can't be, something must be going wrong. Then we had in the same year this famous paper called False Positive Psychology by Simmons, Nelson, and Simonson, where they reported that the severe consequences of selectively reporting data and analyses, and this is where the term p-hacking was coined. And so they realized that all these researcher degrees of freedom, and again, as Lydia mentioned, right, things that people were doing at the time without realizing the effect it was having on their false positive rates, right? And these were not just things that people didn't realize were wrong. It's things that people were told to do by their mentors, right? And so I think we should give people some slack, because people didn't realize how damaging these practices could be. So things like collecting more dependent variables, adding more observations until you find significant results, adding an interaction or dropping a condition. They realized that if you do some, all combinations of these things, your false positive rate, instead of being 5%, can go all the way up to 60%. So this was really a time when the whole discipline, it was like an oh shit moment of not, this is pretty bad. And they did, do this demonstration where they used all these techniques and essentially showed that people were half year and a half old younger after listening to When I'm 64 than Kalimba. Of course, can't happen, but right, you can show anything as true if you slice and dice data the right way. And of course, there were some famous fraud cases. Lydia already mentioned Diederik Stapel. At the same time, there were two other really famous cases of Lawrence Sanai at University of Michigan and Dirk Smeesters at University of Erasmus that really caught people's attention. Some key events happened in 2012. There was a really famous failed replication of a social priming study by Barge and colleagues. And this was priming people. They showed that priming people with an elderly stereotype made them walk more slowly. And so the replication failed. John Barge responded, and it was pretty nasty. I mean, he was pretty critical of the journal standards, of the fidelity of the replication, and the researchers' ability to do the replication, calling them sort of, ill-informed and incompetent. Daniel Kahneman then wrote an open letter calling for the whole field of social priming to do more systematic replications. In the same year, Leslie John and colleagues published this paper on measuring the prevalence of questionable research practice, where they found that a surprisingly high number of researchers admitted to doing things that we now realize are questionable research practice. So these are things like, so the dark bars are self-admission rates. People are admitting this. So things like failing to report all dependent measures, or collecting more data after peeking at the results, and only reporting studies that worked. So again, self-admission rates is pretty surprising. And of course, Lydia has also mentioned this, one of the, I think, strongest indictments was the open science collaboration, which showed that only 36% of the study, that's 35 out of 97, were replicated unambiguously. So now, of course, in the past, more than a decade, there have been a lot of improvements in knowledge baking. We, of course, have pre-registrations where you commit to methods and analyses before conducting the research. There are registered reports where the journal reviews the proposed study before the data are collected, and agrees to publish the results regardless of how the results turn out. So this is sort of an antidote to publication bias, right? We assess the study on the methods and how rigorous it is, as opposed to how the results come out. There's, of course, now more avenues for publishing null results. You can publish preprints, and there's just generally a more focus on doing replications and publishing null findings. There's more team science. So this is where, there's collaboration among a lot of researchers to answer important questions. This also includes adversarial collaboration, which is when researchers who might have competing hypotheses about an effect will get together and design a study together that will help them answer, which one might be correct. There's a push for doing more open peer review. Typically, peer review is a very, it's sort of like a hidden process. People don't know really what's going on. So there's more push to do, like open identity. So people signing their reviews, the reports are open, and then open to participation. So people, more people outside just the editorial team can take part. We now, of course, have things like the open science framework and also other, like the research box, places where we can now, openly share our data, our materials, our code, so that it's available for other people to check and also replicate, right? It makes replications easier. And finally, there's blind analysis, which is quite new, at least in psychology. It's a procedure that's used in physics. And the reason it's, and so what blind analysis is I think it can be a great addition to pre-registration. And what you do in blind analysis is that once you have the data, you essentially change some feature of it. You either shuffle the data or hide certain aspects of it as you're conducting the analysis, so that you don't bias the results one way or the other, right? So any decisions you're making about how to analyze the data are done without knowing what the results will be. And the reason physicists do this is because there's this tendency to look for errors only when the results come out in an unexpected direction, right? So if you realize that you haven't gotten the results you want, you're more likely to check for errors. So there's this bias that can pollute the results, right? So if things come out the way you want, you will not look for errors. So it's sort of an additional guardrail with pre-registrations. It's not adopted that widely yet, but E.J. Wagemakers and his team have published some papers tailoring this procedure to psychology. So if you're interested, I would recommend looking those up. So we have all these new techniques and tools in our arsenal to do better science. And so another project that's sort of near and dear to my heart is this course called Replicability, Transparency, and Evidence in Behavioral Sciences, which I took as a graduate student here at Berkeley and helped teach last semester with Drs. Leif Nelson, Dom Moore, and Joe Simmons. And the idea of this course, it sort of revolves around both learning about open science practices and also practicing the open science practices in this collaborative replication project. And so we had 20 students from all across. So that's Berkeley, University of San Diego, Cornell, but also internationally from, Technical University of Eindhoven, University of Chicago, Toronto. We talked about a lot of the things that you would talk about today, like the replication crisis, p-hacking, pre-registrations. We had some wonderful guests that came up, including Daniel Lockins, Samin Vazir, Yuri Simonson. And the project involved 20 pre-registered replications of construal level theory. And this is a famous theory in psychology, which essentially says that the level of abstraction, like, so the things that are sort of psychologically proximal are construed more concretely than things that are psychologically distant, which are more abstract. And so the topic was decided, with the students. They recommended it, and then we tried to do best practices. So we do this replication doing the best practices we can. We reach out to the authors for comments, take in their comments and make changes. All the studies are pre-registered. Half of the studies were done on blinded data. And of course, we're almost done with the analyses. And after that, all the data, material, and code will be publicly available. So it's been quite rewarding to sort of, learn and teach open science practices and see just how far we've come from in the last decade of doing practice. But here I will take a little bit of a dark turn because there are definitely challenges. So Lydia mentioned benefits. I will mention some challenges associated with open science. So the first iteration of this course happened in 2018, and it resulted in this paper that was published in PNAS. They had looked at the psychological consequences of scarcity, which is where you manipulate people into sort of in a scarcity mindset, like they have less. The original authors of the theory and the original studies published some very critical commentaries on this project, where they were critical of both the method and also the people who were doing the studies. And here I want to point out this general tendency, right, to frame replications as a personal attack rather than a healthy scientific practice. And this has been quite common. People who do a lot of replications face this a lot, where people think that they're being attacked if somebody's trying to replicate your work. Even though we all agree in theory that doing replication is good, this can be a huge issue where people can be quite defensive when their work is being replicated, especially when it's not replicated. So that's one challenge. And I'll give you two more examples of how challenging it can be to do open science. So this is the reproducibility project, Cancer Biology. So this was a collaboration between the Center for Open Science and Science Exchange. It was an 8-year effort to replicate high-impact cancer biology publications published in eLife, which is this open access journal. It was a registered report format, and the authors just faced a lot of issues. There was a lack of transparency and accessibility of methodology. And again, this is cancer research, so they had a lot of difficulty getting access to reagents that they needed to replicate the experiment. A lot of the original authors were not cooperative. They could not get the data and the methods from them. And there were unexpected challenges with the protocols and resources. So things just did not go as they expected. I think some of their cells were, multiplying faster than they expected, and they couldn't change it because of the rigidity of the format. So this is not many experiments had open data. None of the protocols were described sufficiently for them to do the experiments without referring to the original authors. A lot of them required asking for materials, and original authors, a third of them were just not very helpful. And so this points to just the difficulty in doing things the right way. And so they do mention eventually that, there's certain strengths to this because, specifying precisely how the experiment will be done is a strength because it avoids the possibility of biasing the outcomes mid-experiment. But it is also a weakness because in some cases it prevented experiments from being redone in different ways when the results were uninterpretable. And this is a theme we'll see often, where people will pre-register also and then realize that they need to change things. And there's some confusion about what to do when things just don't go as planned. And we know that in science, a lot of the times things don't go as planned, So there's this delicate balance between researcher degrees of freedom and the flexibility that you just need, because science is, not linear and not easy. There's another challenge I will mention that this is related to team science. So there's the Psychological Science Accelerator, which is this large collaboration of researchers from 73 different countries who pool their resources to accelerate the accumulation of rigorous knowledge, right? So the more people you have, the high-powered studies you can run. In theory, just a great initiative. Not in theory, it is a great initiative, but as one example, they ran these 3 large-scale studies, so 73,000 people, lots of resources, right? Lots of time and resources to examine the effects of framing. So how do you frame messages that were related to pandemic-related behavior? They looked at loss and gain framing. That's when do you frame something as a potential loss or a potential gain? They found little to no impact of loss framing on policy attitudes, behavior intentions, or information seeking. Cognitive reappraisal is an emotion regulation technique where you reframe, the message to make it more positive, to sort of mitigate negative emotion. They did not reduce intentions to practice preventative health behavior. Autonomy framing, which comes from self-determination theory, where you try to increase a sense of agency of the participants. And these messages did not influence autonomous motivation or behavior intentions. So the results were a little bit more nuanced than I'm describing, but all this to say that they mostly sort of found what people should not do. But as you can imagine, right, at a time like this, when it's a consequential time and we need people to, take less risks, maybe do more social distancing, it would have been more helpful to know what can be done. So again, great initiative, but can have unintended consequences and can be quite costly in terms of time and resources. So I don't have time to go through all of it, but I will mention, and Lydia will probably touch on this a little bit more in the next presentation. There's also a lot of criticism of pre-registration, that it does not compensate for weak theory. There's also a real risk, but people think that, that it will stifle discovery. And I think there was a comment earlier about this generational divide, and you do see it with people in the older generation mentioning that they think that we will be less likely to discover new things if we can't explore data. And there's this misconception that you can't explore data if you pre-registered. Leslie John and colleagues have also dubbed what they call prediction preoccupation, that there's a certain anxiety with pre-registering and people are really worried that they'll get things wrong. And that they show some results that show that people might be just a little bit more worried about that, and that it will lead them to explore less. Relatedly, there's some arguments made. Barry Schwartz has made this argument that this enhanced rigor may reduce, false positive, but may also unintentionally, increase false negative. So we may not find true positives because the bar is so high. Yeah. And I mean, this can be a whole talk on its own, but of course, opening up science to the public, and especially, there's conversations happening on Twitter all the time. There's a risk of social media becoming another reviewer, where you see cases where research will get criticized on social media and then is, retroactively retracted. And this is especially problematic, I think, when the methodology or the data are not the issue, but it's actually people don't like the conclusions that are being drawn or could be drawn from the data. So just some challenges there. So all this to say, open science is difficult. And yeah, especially in subfields, it can be even more difficult, right? If you're running a 2x2 with online participants, it's sort of easy to pre-register and upload all your data or code. But what if you're doing a 10-year longitudinal study with hours and hours of interview transcripts, right? How do you cannot, well, not that you couldn't, right? But it's harder to pre-register things and be completely open about all the research procedures and the materials. What if you're working with proprietary data, which schools are from companies, right? So not saying that it's not possible, just that there are issues that still need to be, discussed, and yeah, we still need to figure some of these things out. Yeah, it's difficult to be, and of course it's difficult to be completely transparent, and know exactly what's going on. And even if it were possible, it's difficult to check, right? As a reviewer, it is really hard to check everything that you see. Even if everything was openly available, it can be overwhelming for people to check. And as I mentioned, right, it's hard to balance researcher degrees of freedom with the flexibility that you sometimes need. And there's some more discussion coming out now about when is it okay to deviate from a pre-registration and when is it not, provided you are, of course, open about that too. And I mean, to the more human aspect of it, it's difficult to be honest about your own errors, right? And I'm sure some of you who've done pre-registrations, I've certainly done it, where you pre-register something and you're like, duh, like, how could I not know this? That was totally wrong. And so it's right. It's one thing to admit it to you, but I think it can be hard to do it publicly. So, and it just, I mean, doing things openly and transparently, it makes life harder. Right? It just does, if you want to do things, carefully and rigorously and be transparent about your methods and your data and your code. It's a lot of extra work, and you're essentially making it harder for yourself to find significant effects, right? And that's not incentivized, right? And so I want to talk about incentives because they are often invoked, like in the system that we have. It is not adequately incentivized to be open and transparent. And yeah, and it's not just that it makes it harder for you to find significant effects. It also makes it easier for other people to criticize your work if you're open and transparent. So, right, it sort of goes against how the system is set up. So it's difficult, right? It's a huge cost, right? It's a good thing in a healthy scientific environment, but if you're the only person doing it, right, it comes at a cost. So the idea is, hopefully to make it more of a norm. But the other thing, and I completely agree that open science should be incentivized, but the issue, I think, with incentives also is that incentive systems can be gamed, right? This is Goodhart's law, which is when a measure becomes a target, it ceases to be a good measure. So we of course have, more like badges, right? So you get brownie points for sort of publishing and being open about data. But we've seen already that a lot of the times pre-registrations are so vague that there's still a lot of researcher degrees of freedom, right? So they're not really tying your hands in the way they should, but you can say that you pre-registered, right? Or data people say that they're open data, or they'll share the data, but they don't really, right? So incentive systems can be gamed, but more importantly, cutting corners cannot be disincentivized. So I think Samin Vazir, I think at one point has said that if you were a rational researcher, of course you would, cheat because that's right. Like it's hard to, you cannot provide enough incentives, right? People who want to cut corners will still cut corners, right? Nobody will be checking everything that you do or be standing behind your back. So I think, yeah, this is something that I've personally thought about, like when, of course, we've made so much progress and things are getting so much better, but a lot of these issues come down to it, where you can't really incentivize really good practice. So if incentives will do it, like what's missing? And so I thought about it a lot, and then I didn't really know what was missing until I read Cargo Cult Science, which if you have not read it, I would highly recommend it. It's a commencement address that Richard Feynman gave in Caltech in 1974, where he talks about science and pseudoscience. And in it, he compares certain sciences to cargo cults. And cargo cults were these islands in the South Seas, which after the Second World War, so what had happened is that during the war, these people living on these islands had seen airplanes come and bring resources and raw materials and cargo. And after the war was over, they wanted to get the same resources. So what they did is they arranged these fake runways, put fires along it, and they made wooden huts where the controllers would sit. It was manned by a person. They put wooden headphones on them with little bamboo sticks sticking out that were meant to be the antennas. And then they waited for the planes, right? They were essentially simulating what they thought would get the planes to come back. But of course, the plane didn't come back because just because it looks like a duck and quacks like a duck doesn't always mean it's a duck. And so he described that there are certain sciences where they follow the apparent precepts and forms of scientific investigation, but they're missing something important. And what he described, the thing that was missing, was this specific extra type of integrity that is not lying, but bending over backwards to show how you're maybe wrong. And this is a very famous quote by him from the same talk, where the first principle is that you must not fool yourself, and you are the easiest person to fool. And after you've not fooled yourself, it's easy not to fool other scientists. You just have to be honest in the conventional way after that. And so, again, if you've not read it, highly recommend it. We actually have a podcast episode on it as well. And this is really where he's talking about avoiding confirmation bias, right? And after that, you can just be honest and transparent about what you've done. And this is what I thought, what it occurred to me was missing, this idea of not trying to show how your hypothesis is true or not trying to prove that what you think is correct, but really going out of your way to show how you could be wrong, that maybe you haven't, right? Maybe your hypothesis isn't correct. And that I think is missing quite often from the way that we are taught to do things. And in this, he talks about, things that we now talk about quite often in open science, things like transparency, publication bias, doing replications. He also, he doesn't use those terms, but also p-hacking and confirmation bias. So highly, highly recommend it. And so I know this all sounds very quixotic, but right, this is Erwin Langmuir, who is a Nobel laureate in chemistry. The scientist is motivated primarily by curiosity and a desire for truth, right? And the driving force in science is a search for truth. I do think that things like publication and prestige and power should be secondary. And I don't want to discount that that's, again, quite idealistic, and there's realities of lives, but really, good science should be driven by curiosity and a search for truth, right? The goal shouldn't be significant results, but true results. And open science gets us to the truth more efficiently. It's of course costly as an individual, but it is the better thing for science more broadly. And it helps in keeping each other honest, right? Even if nobody's looking, as long as you're open and transparent, somebody could look, right? And that helps keep us honest, and keeping each other honest is important for credible and reliable science. And opening science for non-scientists allows the whole enterprise to stay a bit more honest, because as I mentioned, right, it can be quite easy to get lost in the game. You put one foot after the other, right? What's the next publication? What's the next grant, right? What's the next? So it can be quite easy to get lost in all that. And so I want to end with the last section of Cargo Cult Science, which I think is an excellent way to end this talk. And I am, citing him, so this is not plagiarism, but he ends it by saying, "I have no more time, so I have just one wish for you. The good luck to be somewhere where you are free to maintain the kind of integrity I have described, and where you do not feel forced by a need to maintain your position in the organization or financial support or so on to lose your integrity. May you have that freedom." Thank you.